7.2 Binomial Distributions. Repeated independent trials measured in terms of success or failures are Bernoulli trials, okay? And notice the word by. By generally means two in our culture. So there's by, two options, and those options are success or failure. So you'll recognize this situation when we have two options only, which when we learned about lotteries in the last lesson, lotteries have many options. So it's not just winning the grand prize, there's some other mediocre prizes in there. Okay, a binomial distribution is a probability when each event is independent. In other words, the probability of success is the same on each trial. For me, this came real when I was tree planting, and I was in university and I went tree planting for 3 summers. And it makes good money. It's hard work and it's fun. When I tree planted, I'd tree plant anywhere from, on my normal days, I'd tree plant anywhere from about 2,000 trees in a day to my greatest, which was 4,000 trees in one day. And that would be done in a 9-hour workday with a good company. And if you ever think about going tree planting, make sure you find a good company to work for. What would happen for me is I would plant in a field, in a large field, like we're talking massive farming here. And a quality checker would come around once a day, sometimes every other day. And they would check my land. And he would throw a shovel down on the ground with a string tied onto the shovel. And that string was 3 meters long. And he would walk around and check every tree within that 3-meter distance. And he would do that in 3 different places on my land where he said he was randomly checking my land. Each plot had about 12 trees in it. So that meant that on a normal plot check, he would check about 36 trees for me. And if I planted at a 97% quality level, because not every tree that I planted was perfect. Sometimes I planted them a little funny, or there was there's this crazy thing up north called the Canadian shield, which makes it a real pain to put trees into it sometimes. And so sometimes my trees weren't perfect. The roots were bent, or my tree wasn't standing perfectly straight up, or I'd left a little gap in it or something. And he would quality check that. So my question here is, what is a probability that he would find no bad trees? So if he found no bad trees, that was a good situation for me, because no bad trees meant that they were willing to actually give me an increase in my pay. So what would have been a day where I was being paid 8.5 cents, I would get a 0.5 cent increase on every single tree, which would give me 9 cents instead on a tree. But that was actually good extra money. So what's the probability he finds no bad trees? Well, to find no bad trees, he would have to come into the land, the probability of no bad trees. And he would find, so I'm saying I planted about 97% quality. I'm not sure I planted that well, but I don't know. It wasn't too bad. So that would be 0.97 is the probability that one tree is good. And then we'd multiply that by 0.97 again for my next tree. And the probability my next tree is good is 0.97 if each one is independent. And I'm saying it is, okay? But we could just see this as 0.97 to the power of 36. 0.97 to the power of 36 is 15.8%. So there's about a 15.8% chance that he finds no bad trees at all. So that'd be about 1 in 6 days or so that he would find all perfect trees, and therefore I'd get a pay boost. And I'd say I was probably a little less than 1 in 6 days. Probably once every 2 weeks I'd get that. Okay. One bad tree. So what's the probability of one bad tree? So here it would be 0.97 to the power of 35, because there are 35 good trees. And, which we multiply, there would be one bad tree in the mix. So that's my 3% chance that I plant a bad tree in there. and there's only one of them here. Now the problem is if I write it this way, then what I've said is my quality checker checked 35 trees in a row and found them perfect, and then the last one he found and it was the bad one. But really that bad one could have been the first tree he found or the second tree or anywhere up to the 36th tree. So in how many ways could he find that one bad tree? Well, let's insert this right here. So let's put 36, choose 1, because any one of them could have been the bad tree. And 36, choose 1 times 0.97 to the power of 35 times 0.03 is equal to 29.9%. What's the probability that there are 3 bad trees in this mix? Actually, let's change that to 2 bad trees. So what's the probability there's 2 bad trees? Well, that's, again, 2 bad trees. Well, this time it could be 36, choose 2, because it could be any 2 in the mix that were chosen as bad. It would be 0.97 to the power of 34, because if you found 2 bad trees, there were 34 good trees, right? And then we'd do 0.03 to the power of 2, which gives us 27.5%. Okay. For me, the reality is I could plant, if I had 2 bad trees in the mix, that would actually get me below 95% quality and could actually dock me in my pay. So really 2 bad trees was pushing it. I could only really have 1 bad tree or no bad trees. So I have a feeling they gave me a little bit of grace on the 2 bad trees. So if you add the 3 of those up, that would give you the probability that I pass on a given day, which is about 73% chance that I pass on a given day, which would mean that 1 in 4 days I would not have a good set of trees and I would fail, which would mean that I actually got paid less if I failed. So I was not allowed to fail without getting docked in my pay. So I don't know, I would say that my quality must have been a little better than 97% because I did not get a dock and pay regularly. Okay, the formula for this is the probability of x is n choose x, p to the power of x, and then q to the power of n minus x, where p is the probability of success on any individual trial, and q is equal to 1 minus p, and it's a probability of failure, which is why up here you saw 0.97 was my success, and this was my failure, and the 2 of those add up to 100%. The expectation for my binomial distribution is n times p. So in my example, the expected value here is I plant 36 trees. The probability was 0.97. Expected probability therefore was 34.9. So I would expect, this is about 35. So I would expect that my quality checker would find 35 good trees. All right, a chocolate company manufactures 40% white chocolates and 60% brown chocolates. Chocolates are chosen at random and placed into a box of 10. What is the expected number of white chocolates? So the expected number of white chocolates, well, if 40% of them are white and they put 10 in there, wouldn't you expect 4 of them to be white? It's expected. Well, we can use the formula, but if you already recognize that practicality, we can just skip by that. But n is my sample size, so there's 10 chocolates. Probability of being white is 0.4, 40%, and therefore we get 4. So we expect to have 4 white chocolates in the bunch. B, what is the probability that 2 or less candies in a given box are green? So, okay, let's make a little chart here. So number, we'll call that 2. So 2 or less, that means we could add 2 white chocolates. We could have 1 white chocolate, or we could have travesty and have no white chocolates. I'd be severely disappointed. Okay, so what is the probability? Well, the probability that you get 2 is 10 choose 2. Then we think about the probability of getting a white. Well, there's a 40% chance of getting white, and there's 2 of them, so 0.4 to the power of 2. And then the probability of getting the other, so not white, is 0.6. And that goes to the power of 8, or you can think of that as 10 minus 2. The next one, if you have 1 white chocolate, that means 10C1. We have a 40% chance of it being white, and there's 1 of those. Then the brown is 0.6, a 60% chance. And if there is 1 white chocolate, there are 9 brown. And lastly, we have 10 choose 0. That's 0.4 to the power of, if you had 0 white, that's 0.4 to the power of 0 and 0.6 to the power of 10. You get 2 white chocolates is 12.1%. Probability you get 1 white chocolate is 4.0%. And the probability you get 0 white chocolates is 0.6%, which means the probability that you get 2 or less is the sum of this. And so that is 16.7% chance of getting 2 or less white chocolates. Okay, so this is called a distribution because you can see the distribution here that this is a higher probability that you get 2 white chocolates. That's higher than the probability that you get 1 white chocolate, etc. You would expect that the probability would get higher and higher until we hit 4 white chocolates, and then to get more than 4 white chocolates, we'd start decreasing in our probability. C, what is the probability that less than 2 candies in a given box are white? Well, for this one right here, less than 2 candies, well, less than 2 is this right here. So the probability would be 4.6% chance. Okay? So that concludes the lesson on binomial distributions.